Now, suppose that I have something like that. F is A or B prime C. We know that this is not written in the form of the canonical form. I want to convert this Boolean function in the form of sum of minterm. How we can do it? We say that for each term, we look at to each term and see that what is the missing variable. In the case of the A, how can I convert this A to the minterm if I could add B and C or B prime C prime in this term? Similarly, for the B prime C, if I could add the A or A prime in this term, I can convert this one to the minterm. Now let's do it. I know that B or B prime is equal to 1. It means that if I AND this 1 by A, the result will not change. So as a result, I will have AB or AB prime. On the other hand, again, for the AB, if I AND by C or C prime, which is equal to 1, and C or C prime to the AB prime, I will have ABC or ABC prime or AB prime C or AB prime C prime. Now, if you look at to these terms, this is a minterm, this is a minterm, minterm, and minterm. Now, I could convert A to the minterm for minterm. What about the B prime C? In the case of the B prime, I can do the same thing. I say that for the B prime C, I add A or A prime. A or A prime is AB prime C or A prime B prime C. Now I write all of these terms, minterms, that I have to write just one times all of these one. If I have, for example, both of the A, B prime C, I have to write just one of them. So as a result, I will have ABC or ABC prime or AB prime C up to the end. You can see that I could rewrite the A or B prime C as a sum of minterm. As a sum of minterm. Okay, let's continue. Now, if I write the corresponding minterm of A prime B prime C is M1, A B prime C prime is M4, A B prime C is M5 up to the end. Now, we prefer to represent the sum of minterm of Boolean function in this form. So this form of representation is a sum of minterm. We use from the symbol of the summation, write the index of each minterm that you can see here inside of the parentheses. 1, 4, 5, 6, 7. And this 1, 4, 5, 6, 7 represent that in the truss table, in the first, fourth, fifth, sixth, and seventh combination, we will have 1. In the rest, we will have 0. Okay, now you saw that representing this function in the form of the sum of minterm is too difficult. Question is this: do we have another way to represent the sum of minterms of this function without adding the missing variables? Answer to this question is yes. How? Using the truss table. We say that if I could draw the truss table of this function that you can see, I can say that everywhere I have 1, I can write the minterms. And everywhere I have 0, I can write the maxterm. Easily using this concept, without the adding the missing variables, we can write the function in the form of the sum of minterm or product of maxterm. Now look at this example. I have xy or x prime z. If I want to convert this one to the form of product of max term, I have to convert all of them in the form of the or and convert this one to the form of the and. How we can do it? Using the distributive law. Using the distributive law, we have x or yz is x or y, x or z. Now, if I extend this one in this form, I write xy here, and x prime here, z here, according to the distributive law. Again, if I apply the distributive law inside of these parentheses, I have x prime x, x prime y. You can see that. Same thing happens for this one, zx, zy. For the reverse one, it doesn't matter. Now here you can see that I could convert the and to the or and or to the and to represent in the form of the product of sum. But this is the product of sum. This is not the product of max term. So question is this: what is the missing variable here z? What is the missing variable here y or y prime? What is the missing variable here x or x prime? How can I add the x or x prime to these terms? Using the concept of the actually again distributive law. So we know that x prime or y, if I or z prime, which is equal to 0, to this term, nothing does not change. Again, using the distributive law, x prime or y or z, x prime or y or z prime, I can write. Similarly, for the second term, if I add y prime, for the third term, if I add x prime, I can find all of the max terms. And if I write the unique max term here, I will have m0, m2, m4, m5. And the product of max term is represented in this form that you can see here. This is the symbol of the product, and all of the index of the max terms is written inside of the parentheses in this form that you can see. And this is the form of the representation of the product of max term. Now, now I want to talk about the Boolean functions which is written in the form of the canonical. So look at here. We said that suppose that this is our function f a b c is 1 4 5 6 7. This represents the sum of minterm, which means that m1, m4, m5, m6, m7. On the other hand, we said that m1, the meaning of this term, this expression is this. m1 is 1, m4 is 1, m5 is 1, m6 is 1, m7 is 1. What does it mean? It means that the rest possible combinations is equal to 0. Which one is 0? The numbers that are missing here are 0. Which numbers are missing here? 0, 2, and 3 means that in the trust table of f, 1, 4, 5, 6, 7 is 1, 0, 2, 3 is 0. And we say that if we write the mean term of the variables possible combinations which is equal to 0, we could write the complement of the function. On the other hand, if we take complement of complement, we will have the original one. So it means that if I take the complement from this one, capital M0 dot capital M2 dot capital M3, which is equal to pi of 0 to 3, is representation form of the max term. So from here we can find that the complement of the mean term is equal to max term, and reversely, complement of the max term is the min term. So this is two important concepts that you have to consider. Now, how we can convert these two form of representation together? We saw that everywhere we have summation, convert to the zero, to the pi, sorry, and everywhere we have one, right? Everywhere we have zero, write the corresponding max term. Everywhere we have one, write the corresponding min term. Now, I want to write the trust table of this one and write this one in the form of the sum of min term. You can see that again this is not min term, this is not min term. How can I change this one to the sum of min term? We said that the simplest way is finding the trust table that you can see here. After finding the trust table, everywhere I have one, I can write the min term if I want to represent as a sum of min term. Everywhere I have zero, I can write the product of max term. So these are min term, these are max term. So summation of 1, 3, 6, 7 is written as the f. F prime is 0, 2, 4, 5, and also f is pi of 0, 2, 4, 5. This is a two different form of the representation. Now, in this example, we say that find a product of max term expression. So how can I find the max term expression? This is the sum of min term. This is the min term expression. I want to have the max term. We said that the missing numbers has to be written. The missing numbers 0, 4, and 6. So 0, this is 0, x or y or z, x prime y z, x prime or y prime or z, according to the table that we talked about that. If we want to have the min term expression of this one, again we say that the missing numbers, which are 0, 2, 5, and 7, are the summation, and the corresponding expression of the 0 is x prime y prime z, corresponding of 2 is x prime y z prime up to the end. So this is the meaning of the min term and max term. As another example, here the trust table is given. Again, we want to identify the min term and max term. Again, here is 1, 1, 1, 1. It means that M1, M3, M4, M6 can be written. What about the max term? Everywhere we have 0. M0, M2, M5, and M7 are the max terms of this function. That was the canonical form. Now, I want to talk about the standard form of the Boolean function. We said that we have two different types of representation for the standard form, sum of product and product of sum. Here you can see that we have sum of products because the variables are product with together here and here. But because in these two terms, we don't have the z, and here we don't have x or z, these are not min term. So in this case, we say that we can represent these functions in the sum of product expression. So the configuration of this type of representation is two-level implementation. If we have this function, want to draw the digital circuit or logic diagram, you can see that for the xy and x prime yz prime, we can have two AND gate and or all of them. Similarly, for the case of the product of sum, we can say that if we have something like that, again, these are not the max term, and we can implement these two in this form, or, and. So you can see that we can redraw the circuits of the SOP or POS in the form of the two-level structure of gates. In the previous one, in the case of the sum of products, you saw that we had AND gate in the first level and OR gate in the second level. In the case of the product of sum, we have OR gates in the first level and AND gate in the second level. In the case of the non-standard form, we can say that if we have something like that, this form of representation is neither standard nor canonical. So we call this one as the non-standard form. If I draw and implement the logic diagram of this Boolean function, you can see that we have to use from the actually more than two level for representing this function. So why we don't prefer to use from this type of the representation? Because you can see that in this pass we have three gates. So the delay time of this pass is higher than the delay time of the two-level implementation. Because if we have two-level implementation, we will have two gates, and we know that each gate has delay time. So it means that the delay time of this pass is greater than the delay time of the functions that are actually written in the form of SOP or POS. So as an example, if I want to represent this function, implement this function, you can see that in this form we can do it. Here we will have BC prime, AB, ACD, so the result will be ORed in this form that you can see. So up to now, we talk about the positive logic. What was the positive logic? The positive logic is this. If we have low level, we consider this low level by 0. If we have high level, we consider high level by 1. But we can have the another type of the logic, which is called as the negative logic. In the negative logic, we say the low level is considered as 1 and high level considered as 0. So in this case, we can convert all of the concept that we have learned up to now from the positive logic to the negative logic. Suppose that if you look at this trust table, low, low, the output is low. Low, high, the output is low. High, low, the output is low. High, high, the output is high. If you look at this trust table, this is the trust table of the AND gate, which is written in the form of the positive logic. Now the question is this: can I convert this positive logic, this AND gate, to the negative logic? Yes, we can do it. How we can do it? Using this concept. If all of the zeros converted to the 1 and all of the 1s converted to the 0, you can find the trust table of the AND gate in the negative logic. How we can represent the actually AND gate in the positive? So you can see that the AND gate also represented in this form in the logic OR gate, but with the actually negative in the input and output. So this is form of representation of the negative and positive logic.